By using a specific trivial puzzle, I'm going to attempt to shed some light on the hidden layers of complexity. Two trains, 100 kilometers apart on the same track, approach each other at 50 kilometers per hour. A flight named Gojo starts at the front of one train and flies at 100 kilometers per hour to the front of the other. When it gets there, it turns around and flies back towards the first. It continues flying back and forth till the two trains collide and the flight gets caught in between. How far does the flight travel before it gets squashed? Go on, take a bit to pause and ponder and have a go at it. Now, assuming you've done that, if you go to 100 kilometers, well, I commend the effort, but you didn't pay proper attention to the question because the flying question is Gojo Satoru, and with his position of limitless technique, the trains would never collide. Okay, now putting aside the Jujutsu Kaisen reference and being serious, if you got to 100 kilometers as the answer, then great job, right? Now let's head on to the solution. There are actually two ways we could tackle this problem. One requires just foundational math skills picked up in the arithmetic class, while the other requires slightly more advanced concepts typically seen in pre-calculus. This solution is fairly straightforward. First, since the flight is in no way affecting the motion of the trains, we can simply remove the flying question and observe just the two trains. The trains are 100 kilometers apart and traveling at 50 kilometers per hour, right? Now we ask ourselves, how long would it take the two trains to collide? Since the trains are traveling at the same speed, then it follows that after a certain time t has elapsed, they would have both traveled the same distance. Let's observe that. At the point of collision, we know for a fact based on what we've gathered that this is going to be exactly at the halfway point. So now, how long would it take each train to travel? Well, using one of the most memorized formulas in basic sciences, we have distance equals speed times time. Rearranging, we get time equals distance over speed, and so 50 over 50 equals 1. Hence, it takes the trains 1 hour to collide. This means whatever fun Paul Gojo was having has to end exactly 1 hour after it starts. Finally, answering the question directly, how far would the fly have traveled? You simply use the formula and we have distance equals speed times time and we get 100 kilometers. Good. Please note that the sheer amount of simplifications we've made here is enough to make a physicist go crazy. We disregard the inner resistance of the medium, assuming the flight can withstand such forces that will arise from instant acceleration and deceleration associated with making such drastic turns. I'm sorry, Einstein. Now let's approach this from the alternate point of view. We are told to find the total distance to be covered by the fly before it gets squashed. The distance covered in each leg is equal to the distance covered by the fly plus the distance covered by the respective approaching train in that leg. But how, you may ask? For some visual illustration, let's have the journey of the first leg play out. These two action points have been placed here to represent the initial positions of the trains. The distance between them is denoted by S leg 1. Alright, let's resume the motion. And as you can see, the distance between these 2 points is equal to the sum of the distance covered by the fly and the distance covered by the respective approaching train. But actually, we could simplify our equation. Because the fly is traveling twice as fast as each of the trains, the distance covered would always be twice that of each of the trains. Or conversely put, because each of the trains is traveling half as fast as the fly, the distance covered will always be half that of the fly. That results in the distance of the fly in this first leg being 2/3 the initial distance. Hence, leaving the distance covered by the approaching train to be 1/3 the initial distance. As the flight begins leg 2, we need to be aware that not only has the train to the right covered the distance 1/3 the initial distance, but also the train the fly is now moving towards. This leaves the available distance as 1/3 the initial distance. Again, we shall visually illustrate. Now let's allow this go on a few more rounds. It's clear that a pattern is being formed. The distance on each round is being reduced by a third, and based on the argument in the first leg, this process continues without end. In essence, It takes the fly infinitely many rounds to complete this journey. But how on earth does this make any sense? Right? Not to digress too much from the main points of this video, I urge you to look into Zeno's dichotomy paradox. Okay, so this term we have here is given as the partial sum of the geometric series. The total distance traveled by the fly is given as the sum of the infinite geometric series. Using the formula, where A is the first term in the series and R is common ratio, we get 100 kilometers. And this is exactly the same as the answer from the easy solution. By the way, there is a famous story, perhaps apocryphal, about this problem. It was posed by a mathematician to the polymath John von Neumann. The mathematician knew the quick solution to the problem and wanted to see von Neumann struggle with it. After hearing the question, von Neumann gave the correct answer within a few seconds. Interesting, said the first mathematician. Most people try to sum the infinite series. To which von Neumann replied, "What do you mean? I took the infinite sum of the series." Giga Chad. Obviously, in the real world, with so many moving parts and much more constraints to consider, this simple problem evolves into a much more complex beast. Let's in fact briefly consider one of these factors. What if air resistance is introduced to the problem, and the fly speed varies directly as a consequence? Now, the problem shifts to the physics domain. I promise that's the last Jujutsu Kaisen reference. To do this, we have to model air resistance and how it affects the motion of the fly. The air resistance, or drag as it's sometimes called, can either be linear or quadratic. In the context of this puzzle, the quadratic drag much closely suits the motion of a fly, as linear drag is a reasonable approximation only for very slow motion, objects moving at very slow speeds, or moving through a very dense medium. Let's have a go at the quadratic drag variant of this problem. Again, greatly simplifying, we're going to assume all the forces in the vertical direction balance out and drag only affects the motion of the fly in the horizontal direction. The force of drag in the horizontal is given to be proportional to v squared. Since the force always acts in the opposite direction to the fly, we have F equals to minus cv squared, where c is the coefficient of drag and v is the speed of the fly. This can be rewritten as m dv dt equals minus cv squared. It is a differential equation and it is set up in a way that is naturally suited for the separation of variables technique. By applying this technique, we have the following. Where the Greek letter tau has been introduced to replace the combination of constants, got enough to simplifying this equation. And then by integrating one more time and setting the initial horizontal position to be 0, we have this expression, which we can use in a contrived case to model the fly's horizontal position with respect to time. Just a single change, adding air resistance and restricting it even further to be only effective in the horizontal direction, transformed the simple problem into a slightly more complex one, requiring some advanced tools from a mathematical toolkit. What starts out as a simple puzzle about a fly and two trains turns out to have layers, from clean arithmetic to infinite series to some physics of real-world motion. And this isn't rare. Many problems in science and math hide surprising depths beneath their seemingly simple surface. Think of the n-bodied problem in physics, impossible to solve exactly once three bodies are involved. A Conway's game of life, a few rules on a grid, yet possessing the feature of Turing completeness. Or Fermat's last theorem, a simple equation that resisted mathematical proofs for over 300 years and required modern, intense graduate level math to prove. The list of problems exemplifying hidden complexity behind apparent simplicity goes on and on. Hidden complexity isn't the exception, it's often the rule. So next time you see a simple problem, ask yourself, what layers of complexity might be hidden?